quick sell car dealership has been using 1-minute spot ads on a local TV station. The ads always occurred during the evening hours and advertised the different models and price ranges of cars on the lot that week. During a 10-week period, the quick sell dealer kept a weekly record of the number of TV ads versus the number of cars sold. The data is provided on the right. Here are the results of the weekly television ads. The manager of the dealership believes there's a strong relationship between the number of ads shown on TV and the number of cars sold. We want to determine the correlation coefficient, association, and strength of this graph to refute or support the manager's thinking. Well, the correlation coefficient is 0.92. Since it's positive, we know that there's a positive relationship, meaning that as the number of weekly ads increase, the number of cars sold also tends to increase. 0.92 falls in a very strong correlation. This week, the manager only has enough money in the budget to run 12 ads. How many cars could he expect to sell? To help answer the manager's question, we will be making a prediction. Because the data is of the linear form, we can model the relationship between x and y. A line that describes how a response variable y changes as an explanatory variable x changes is called a regression line. Keep in mind that the line will be wrong in the sense it will not match reality exactly. You're probably accustomed to seeing the linear regression line looking something like this: y equals mx plus b, or y equals ax plus b. The general form for a linear regression line in AP statistics is y hat equals a plus bx. Y hat is the predicted value of the response variable for a given value of the explanatory variable. A is the constant, it's the y-intercept, the predicted value of y when x equals 0. And b is the slope, the average amount that y changes when x increases by 1 unit. Before, in y equals mx plus b, b was the y-intercept. In this case, the b is the coefficient for x, which is the slope. So no matter which formula you're using, the number in front of x is the slope. We want to make sure to include the hat on the y. Y equals ax plus b defines y as the actual y value. We're making predictions, so we're going to use y hat. So here are the results. The regression line for this data is y hat equals 6.54 plus 1.01x, or we can substitute the words instead. Cars sold hat equals 6.54 plus 1.01 times the number of weekly ads. If we use the variables y hat and x, please make sure that you define what y and x stand for. So let's interpret the slope and the y-intercept. The y-intercept is 0, 6.54. 0 is the x value, which is the number of ads, and 6.54 is the y value, the number of cars sold. If the dealership used no ads, we would expect 6.5 cars to be sold that week. We expect that because it is a prediction. We can't say for sure that 6.5 cars would be sold that week. The slope we know is the average change in y as x increases per unit. So the average number of cars sold per week increases by 1.01 for each additional ad per week. It's very important that you include the word average when describing the slope. Predict how many cars would be sold if 12 ads were ran next week. 12 ads being the x value, we substitute that value into our linear regression model, and we would expect them to be selling 18.66 cars. Predict how many cars would be sold if 40 ads were ran next week. The linear regression line would not be appropriate to predict 40 ads because 40 ads is outside of the range of data values collected about the number of ads. If you look in the table, the range of data values for the ads is 0 to 28. 40 falls beyond that. When you use the regression equation to make a prediction about a response variable that is outside the range of data values, it is called extrapolation. This can produce unreasonable results. Below is the scatter plot and its linear regression. Interpret the slope and y-intercept. The y-intercept is 0, 0.95. X is 0, which is the miles driven. Y is the toll in dollars, which is 0.95. So our interpretation is we expect that after driving 0 miles, the toll would be 95 cents. In other words, we expect a 95-cent flat fee. The slope is 0.05. So there's an average increase, because it's positive, of 5 cents per mile driven. The slope is 0.438. there's an average increase, because the slope is positive, of $438 for every additional 1,000 miles driven. The reason it is 438 is because you can see on the axis that the repair costs are recorded in hundreds of dollars, and on the x-axis the mileage is recorded in thousands of dollars, or thousands of miles. So $438, 1,000 miles. Below is the software output for the information from the last example. Notice that the constant is the y-intercept, and the number below it is the slope. So if we were to write the equation, it'd be y hat equals negative 2.60 plus 0.438x. Below is the data output for minutes played by the Los Angeles Lakers starting lineup compared to the number of total points each scored. Write the linear regression model and interpret its slope and y-intercept. This is the linear regression model. The constant is the y-intercept, negative 607.2. The number next below it is the slope, 0.7007x. Writing it with words instead looks like this. The y-intercept is 0, negative 607.2. If an LA Laker played 0 minutes, we would expect them to score negative 607.2 points. This does not make sense, so there's no meaningful interpretation here. The slope is 0.7007. This means there's an average increase of 0.7007 points for each minute played.